So in this section, we've got really something different to look at. We've got a geometric theorem that we can prove using this induction method. And what it says is, if you have a checkerboard and its dimensions are 2 to the n by 2 to the n. Right? So it's 2 to the n squares long and 2 to the n squares deep. Then if you take out one square, it doesn't matter where that square is, if you pull one square off of that checkerboard, then you can tile it, which means you cover it with right triominoes, which are what you see over there on the right hand side, right? It's got that right angle shape, right? And you can think of it as being made up of 3 kind of subsquares here. That's the tripart. Okay, so how can we do this using induction? Well, we have to look at our base case, right? So our base case would be n equals 0. If we do that, what's the size of our checkerboard? Well, it's 2 to the 0 by 2 to the 0, which is 1 by 1. Okay, well that's a single square, right? And if we take away a single square, then there's nothing left. So can we cover this with triominoes? Well, with right triominoes. I want you to think back, way back to an earlier lecture where we talked about something called a vacuous truth. You remember the example I used was, what if you know something is true for every student in a room, but there aren't any students in the room? Then was the statement true or false? Remember, we saw that it was in fact true, and that's the exact same situation we have here. If there are no tiles available to cover, can it be covered with this shape? Well, the answer would have to be yes, and that covers the base case. Now, if you're a little unconvinced by that, that's okay, right? Let's say we go up to the next step. Let's say we look at n equals 1. Okay, well then that gives us a 2 by 2 square. And well, can we do it with a 2 by 2 square? Well, yeah, we can, because I've got some examples here for us to work with. There's only 4 ways we can remove a single square from these shapes. We can remove this one, in which case, yes, that can be covered with a right triomino, or we could remove that square, in which case, yes, it can be covered, or we could remove this one or this one. So in all 4 of the possible scenarios that we could come up with here for removing a square, what the checkerboard that's left can still be covered by this right triomino. Okay, so yeah, even if you're sketchy about that whole vacuous truth thing and you're not comfortable with that n equals 0 case, we can still do it for n equals 1. And you will sometimes see this in proofs by induction. Technically, you only have to prove that n equals 0, that first case, but sometimes you see a proof will go ahead and kind of do the second one as well, like we did here. You do it for n equals 0 and n equals 1. All right, so that's the base case, right? Now, where do we go from here? Well, so sorry, I had to go to a new page, right? We were really out of room on the last one. So I've got a diagram here for us to work with, and what we need to show is if a 2 to the n by 2 to the n board with one missing piece can be tiled with triominoes. I'm abbreviating a little bit because I don't have a whole lot of room. Then a 2 to the m plus 1 by 2 to the m plus 1 board, again with one missing piece, can be also, right, can also be tiled with triominoes, right triominoes. So here's how we're going to do this, right? I'm going to take my board, and remember, this board is 2n plus 1 by 2m plus 1, right? So it's the bigger board that we're supposed to be proving this statement about. And I'm going to divide it in half both ways. All right, so then now I have 4 subsquares. How big are these subsquares? Well, if the original one is 2n plus 1, and my subsquares are half of that, well, look at that. That's making me feel good about this, right? The individual subsquares there are 2 to the m by 2 to the n. And that's what my inductive hypothesis is talking about. All right, so we've got this big square. You notice I just kind of randomly picked a spot and removed a square from down there. So it's a 2m plus 1 by 2m plus 1 with 1 square missing. Now this bottom square down here, bottom right, this one is a 2 to the n by 2 to the n square with 1 square missing. Well, according to our induction hypothesis, this one can be tiled with right triominoes. Okay, so how about the others? Well, here's what I'm going to do. I'm going to remove some squares from the other ones. I'm going to do it really carefully. Right? First, I'm going to take out that square. Right, when I do that, this upper right-hand square is 2 to the n by 2 to the n with 1 square missing. So again, by that induction hypothesis, that one can be tiled. All right, now I'm going to do it again. Now I'm going to pick this square. Now this upper right-hand corner is 2 to the n by 2 to the n with 1 square missing. So this one can be tiled. Now I'm going to take away one more. I'm going to take away that piece right there. Right? And now I've got the same situation. The bottom left square is 2 to the n by 2 to the n with 1 square missing. So again, it can be tiled. So at this point, I have tiled the entire board except for those black squares. But those black squares are a right triomino. So if I take a right triomino and I rotate it and flip it, I can cover up that piece, and now I've covered up the entire board, which is what I needed to show that I could do. Right? So that finishes the proof. All right, so hopefully now you're starting to get an idea of first how proofs by induction work, and second, kind of how powerful this technique can be. Right? It's not limited to just doing algebraic things or even just to number theory things, which sometimes feel kind of algebraic. Right? We can actually apply this to all sorts of different fields. So this is kind of the end of our discussion of induction directly, but there are still other kinds of induction that we're going to talk about. For example, in the next series of lectures, we're going to kind of go in a slightly different direction and talk about something called strong induction.